Let me just run through this first one with you, and then I'll turn you guys loose and see if you can handle the other ones. I just want to do this to make sure you're doing okay. So you've seen it one more time at least. So the first thing I always do, and sometimes the AP test will do this for you, sometimes I'll do this for you too, is the first thing I'm going to do is I'm going to get rid of this awkward notation with this f and a little -1, because that almost looks like 1 over f or something. That's not what it means. It means the inverse of f. And so my first step is to say the inverse of f, I am going to rename it, and I'm going to call it g. So the inverse of f, I'm going to say is g. So you might even want to write inverse of f equals g, just so that you can use one for the other without worry of being confusing. All right, and then maybe the next step would be to either remember or develop the formula to find the derivative of the inverse. And so let's see here. If g is my inverse, I would say that g prime of x equals, and this would be where you'd recall it perhaps, it's 1 over f prime of g of x. And as I mentioned in the video, you can choose to memorize this, and hopefully you do it enough times, write it down enough, you just have it naturally memorized by using it, or you can choose to develop it. Hope is if you just have one of those blanks in your memory and you forget how to do this, you could always develop it, right? That's where we'd start. We're looking for the derivative of the inverse at x equals 7. So pretty simple instructions, not necessarily easy steps. G prime of 7 then is what we're really looking for. So we got 1 over f prime of g of 7 because I'm plugging a 7 in for all my x's. And here's kind of your first major hurdle because g of 7, you think, awesome, g of 7, that should be easy. All I have to do is plug a 7 in for x in the g function and do a little arithmetic and I'm done, except there is no g function. There is no g function for you to do all that with, which would make it super duper easy. The truth is, because this is a 1-to-1 function, because f of x is 1-to-1, the inverse of f would also be a function. So you could actually find the inverse pretty easy by doing that whole flip the x and y and solve. But most of these, you don't have that ability because they aren't 1-to-1. And so it would not work out so well. Here's what I would do. I would look at this 7, and I would say, all right, well, g is the inverse of f. And here's that principle we talked about a second ago. The inputs for g would have to be the output for f. So instead of taking a 7 and trying to plug it in for x in a g function, which I don't have, I'm going to take the 7 and plug it in for the output of the f function. So it would be 7 equals 2x cubed plus 5. This is actually a pretty simple equation to solve. You subtract 5, divide by 2, and cube root. Often, though, you're going to have to do a little bit of guess and check, and this would be a pretty easy one to guess and check, too, wouldn't it? X has to be 1. So if the input for g is the output for f, well, then the input for f would have to be the output for g, right? They get switched around. So then I think I could confidently say that g prime of 7 equals 1 over f prime of 1. The good news here to finish this out is I do have f of x, and so finding f prime won't be too hard. Maybe I come over here and say f prime of x is equal to 6x squared. Therefore, f prime of 1, which is what I'm looking for, is 6. Therefore, g prime of 7 is equal to 1/6. There's a lot of inputs and outputs getting switched around and things like that in there. I hope I didn't confuse anybody. Hope I helped. Let's see how we're doing. Why don't you guys try number 3? And this will be a little more challenging. The equation a little more complicated. See how it goes. Here to help. All right, let's look and see how this went for you. So, maybe, like I said, suggested on the last one, that instead of using the awkward f with a little -1, we say that, hey, the inverse of f, we're just going to call it g. And do you guys know that you can do that on any, really, like AP test, my test, like really any math test? If you establish a relationship, as long as you make it clear, you can use that relationship any way you want, right? You can make stuff up, name something different, it's okay. Just be consistent with it. Okay. So then what we're really looking for here is g prime of -15. So maybe you write down this first step right here. And so Johnny was talking about, like, how would you, award points for something like this on a quiz or test? Hopefully you just get everything right and you get, full credit. But let's say you make some mistakes. How would that go? So I'm going to be looking for this relationship. So if you've got this relationship between the inverse of the derivative of the inverse and what it should be, essentially you've got the formula either developed or memorized, or you understand the formula. That's always going to be kind of our first point and kind of the gateway to other points too. So then once I've got that set up, I've got to recognize that if the input for G is negative 15, that means, I don't know what they're doing either. That means the output for F is negative 15. So I'd come over here and I would find negative 15 equals 2x cubed plus x plus 3. And this is where people that have sort of like thought, it's no big deal. I'll just sort of switch the x and the y's and solve for y. And that'll get... It doesn't work so well, does it? This is not an easy equation to solve. It's not a quadratic, it's a cubic. And it's, I don't know if you're going to be able to do the rational roots theorem. Maybe it's either going to take you forever or it's not going to work very well. And so to me, the most efficient process would be guessing and checking. I think I mentioned in the past, I'm not going to give you crazy guess and checks. Like Jake, I'm sorry if you only would have guessed negative 37 sevenths. I mean, why didn't you think of that? What's wrong with you?
That was going to be our next guess.
It's like, give me a couple more minutes, I would have got there, that kind of thing. We're going to keep it around 0, right? Plus or minus 2 or 3 or 4 at the most. Nice whole numbers, integers, that kind of thing. No crazy stuff. So as you started to take some guesses here, what started to make sense? Negative numbers, right? Because it's negative 15, and then negative 2, sure. Negative 16 plus negative 2 is negative 18, plus 3, look, it's negative 15. And so you'd say negative 2 is equal to x. And so then, Johnny, as far as points go, I'd look at it and say, all right, did they make the connection between the whole input-output thing? And did they figure out that x has to be negative 2 for this relationship to work? So this would be kind of your second point. So it'd be a 3-pointer. And then your last point would be essentially, can you figure out f prime of negative 2? So f prime of x is equal to 6x squared plus 1. F prime of negative 2 is equal to 25. And therefore, our objective, which is that, is equal to 1/25. What do you think? Questions, concerns? Raymond?
This is kind of a silly scenario, and it probably wouldn't happen.
Okay.
Let's say you're on the AP test, and there's a guess and check thing like that, and you're like running out of time, and you never found the proper guess. Could you just choose a false number, and then go on with the next part? Would they give you partial credit?
Good question. Yeah. So this is obviously a free response scenario, obviously. And I don't know that it would apply directly to this one because I don't think this is going to show up on a free response all that often, if ever. But in cases like that, you want to be really, really careful in the sense that the answer to your question is possibly. It could possibly work out okay because you can have that propagated error thing, However, if the answer to say part A, which gets used in part C and D or something, if your answer for part A either clearly has nothing to do with part A at all, you didn't even really attempt part A, you're on thin ice for sure. But then where you're going to definitely run into issues is if it causes you to trivialize, right? So let's say you just throw out x equals 2 in part A. You're just sort of educatedly guessing, kind of, sort of, but you're not sure. And then you use 2 in C and D. And it just so happens that the number 2 causes something that equals 0, which totally changes the nature of the question. Now you're not going to get that propagated error stuff. Yeah. But I would say if you have the time and you want to try that, that's better than leaving it blank. Whatever you do, don't tell them what you're doing. For goodness sake, don't be like I've seen people write notes like this in part A. They'll be like, I have no idea how to figure this out, so I'm just going to guess 5. And so we know you have no idea what you're doing, right? And so we're okay, so they guess 5. What's that going to do these other parts? Don't tell them that. Don't take that out of the equation of does this person know what they're doing? Don't just say, I don't know what I'm doing. Just say, you write some stuff down and I think it's 5. I don't know if you know what you're doing or not. I mean, you clearly got it wrong, but you might know what you're doing and made a mistake. Yeah. I don't know. I have to investigate that. So some people write that. I'm like, come on, just have a little gamesmanship. So the answer to your question, unfortunately, is sometimes. Okay. Just be careful, and it's very possible. Okay, any other questions?
Would this ever be on a multiple choice question?
I would say 90-something% of the time it would be. Yeah, an inverse, derivative of an inverse. I mean, honestly, I can't think of a time when it's ever been on a free response. I'm probably not remembering, there might be one time, but I mean,
Is it 'cause
I hate to admit it, but I have like most of the last 25 years, like more or less memorized, not to the point where I could just reproduce them, but I'm like, oh yeah, that one, oh yeah, that one. I don't think I've ever seen this on that. It would be very rare, and it would, I mean, yeah, if you know the formula, it's like a done deal, right?
You can't make like part B or part C.
Unless you're
Well, you could. I mean, you could have some function and do multiple things with it, but they wouldn't necessarily have a nice connection, like a nice flow to it. It would feel like 3 or 4 choppy questions, and they usually try to make it flow more or less.
Do you help make the problems or just grade them?
I have actually written 2 of them, and they highly edited them, and I was upset. Whatever. No, I didn't make the potato.
How did they highly?
I think mine got used for multiple choice. Yeah. No, you cannot. I know the person who made the potato question, though.
What's he like?
I worked with her, it's a she, so I worked with her last Christmas, and people were still, I didn't know, other people knew that she had done it, and I didn't know that she had, other people were like making fun of her. They're like, thanks for writing like the worst question in the history of question writing, or whatever. It was actually a pretty good question, but it was hard. Like there was a lot of people that were very uncomfortable with it.
Like
So
white potatoes out of everything.
Yeah.
The potato.
I don't know who wrote the escalator question though. I don't know who did that one. All right. So then number 4, if you guys haven't already looked at that, please take a look at number 4. Give you a couple minutes here to look at that one as well, and we'll be done with this part. Here is numero quattro. Try to tie this one off. Hopefully it's all, going okay. There we go. Okay, so like before, I'm going to say that the inverse of f has been renamed to be the function g. And so since I'm looking for the derivative of the inverse of f at 0, what I'm really looking for is g prime of 0. And I'm going to want to write down this in order to get started. That's my relationship. Please notice the good notation here. For example, what I'm about to write would be really terrible notation. It might seem like no big deal, but what's so wrong with that? Look what I wrote.
It needs to be G of 0.
Yeah, like if x is 0, that means x is always 0 for this particular part of the expression. So if I plug in a 0, that means the x has to be 0 everywhere. So that would be bad news. That would be good news. All right, so g of 0, if the input for g is 0, that means the output for f is 0. So we would write 0 equals 2x to the 5th plus 4x minus 6. And I'm really hoping that by a quick inspection, you can look and say x had better be 1. I was like, does that look like a... I don't know, whatever. Oh, I got the 5 plus the 1. There you go. Sorry. X equals 1, yes. All right, so that means g prime of 0 is really equal to 1 over f prime of 1. And since I've got f right here, f prime is fairly easy to find. 10x to the 4th plus 4. Therefore, f prime of 1 would be 14. Did you guys all get 1/14? Any questions? Any questions at all? Okay. All right. So I am going to do a little skippage here. This is going to fit in just fine, and I know that I need to make sure that we are on schedule because there's very little wiggle room, and who knows if there's going to be some lockdown drill or fire drill in the future or a snow day. I am not going to sit and wait for that to happen and wreck our calendar. So if you guys would, go into the future a little bit, go past this stuff, that's for tomorrow. Skip on past that. We'll do that stuff later on. Not yet. We're not going to do any arctangents. Not going to do any integrating. We are going to finally land our spaceship right there. Let's do this. So this is the no crash landings. Smooth landing. This is the very end, right before the extra practice stuff. So of course, yeah, this introduces all kinds of new stuff. Do you guys remember when you first, maybe you were like in 7th or 8th grade, or maybe you saw your older brother or sister's math book and you saw S-I-N and you're like, sin? Like, how could math be sinful or whatever, you know? Like, seriously, like I've had some people, like I've had some algebra students, like there's like some of this stuff written up there and they're like, sin? Really? Like, are you over-Christianizing math? Like, really? Just stop talking right now, because you don't know what you're talking about. Anyways, whatever that's worth, this introduces some more jokes like, oh, gosh, you know, that kind of stuff. Sinha and what, I don't know, whatever. So I want to give you guys a basic primer on this. Hey, listen. This would be a bad time for you to be distracted because I'm fairly certain none of you have ever seen this before in your life. And so I want to kind of help you through this and explain the whys, whats, whens, and hows. Okay, so A, why? Why are we going to study this? So here's the reason why. In a standard college calculus 1 class and or college calculus 2 class, which is what you're in right now, this is pretty standard fare. Okay, hyperbolic trig functions. And so I am hoping that when you get to college, if you end up taking some Calc 3 class or some other higher level math class, linear algebra, whatever it might be, and your teacher's like, okay, hyperbolic sine, you're not like, what? You're just like, what? Oh, yeah, we did something with that, right? So I'm trying to plant just a little bit of seed in your brain to later on when your professor says something about this. Hopefully, unlike some of your other colleagues that had A, B, and B, C that hadn't seen this, you'll be able to be like, oh yeah, this is a little bit about what it is. And instead of feeling like completely lost, you'll feel just like a tiny bit lost, and you'll be able to do okay. That makes sense? So I'm not giving you like the full treatment of this, and we're not going to cover every single thing. We're only really going to look at these 2 hyperbolic trig functions, sine and cosine. There is a hyperbolic tangent and cosecant and so on and so forth. But if you can get the basic plot of what some of these are, that's at least going to be a platform from which you can move forward instead of being like, what? My teacher never taught me about this. That's the why. Question, Emma?
Will these be on the AP test?
We'll get there in a second.
Okay.
Do you read that cosine HX or like?
Hyperbolic sine.
Oh.
Hyperbolic sine of x. Hyperbolic cosine of x. Although if you say kosh or sinha, like, we'll know what you mean. Sinha. Okay, so that's, guys, that's the why. The how is this going to be assessed? This is kind of like Newton's method. The only time I'm ever going to assess anything about this would be on the Unit 3 test, which is not the next one, it would be the one after that. So that'd be the only time I'd ever assess this. I'm not going to assess this on the final exam. It is not assessed on the AP test. It's not part of the curriculum framework for the AP. And so, like I said, why? I'm just trying to give you a small taste of this so that later on you're not like, I feel completely lost. I never heard of this stuff. You'd be like, yeah, I've heard of it, and I might have to do some work to, a little catch-up work, but you've heard of it at least. You understand maybe some basics about it. What are we going to do with it? We're just going to work with it a little bit today. This will probably be our only day unless you have questions on it later. Assessed on down the road when we get to the Unit 3 test. Does that make sense? And I am really hoping that there are at least some of you in here that are like, you know what? I am interested in a good grade in AP class. I am interested in making a 5 on the AP test. But more than that, I think math is kind of cool, and I like to explore different areas of it. And some areas I might walk this way and be like, ooh, I don't like that area of math. Oh, I like this way. This might be one little piece where you're like, later on, you're like, that was actually kind of cool. This is highly, highly applicable. Your cell phones would not work if we didn't understand this. Seriously. Like the ability to use GPS and track where you are and know where the cell towers are and all that stuff. Seriously. Okay, so these naturally come about when you find the solutions to certain types of differential equations. And without us being able to do things like this, we would be lost on how to program the satellite, the phone, the whatever, to communicate with each other and make it all work out. Okay, so highly, highly applicable. I'm just teaching you the basic stuff here. Okay? And actually, certain bridges wouldn't function without this either. Like a suspension bridge, you guys know like the cables, I'm going to make a little hand motion here. The cables form like this kind of a thing. and you've always been told that that's a parabola, or maybe you thought that that was a parabola. It's actually called a catenary, the shape of it, which is directly related to these. I mean, these are highly applicable. And so if you end up being an engineer someday, or maybe a programmer of some kind, this very well could be something you would need to be good at. So anyways, just a thought. So I do want to point out some real basics here and connect this back. You can write this down if you want. I'm going to do my best to just sort of fit this in here. I am going to do my best to draw in a lovely circle over here. There's a circle. I'm pretty good, aren't I? Yeah. I have, or I also have a circle tool. So anyway, so a circle is something we're all quite familiar with, and specifically the unit circle. So if now you can tell I'm not that great at drawing these. It's a little bit off center, but hopefully you can forgive. That's just way too bad. They are very straight lines. There we go. I'm going to go with that. So if you have the unit circle, let's see if this is familiar to you all. Like if I just picked a point out here and I traced the angle leading to that point and I called that angle theta, then wouldn't the coordinates of that point out there be cosine of theta, comma, sine of theta? Given that this is the unit circle, and that would be true all the way around the unit circle. So I've got this angle, I want to know the point, just go cosine of that angle, sine of that angle, and I've got the actual xy coordinates for that point, right? So the hyperbolic sine and hyperbolic cosine are kind of related to this in that if you have an angle from the origin out to the graph, like theta here, then hyperbolic sine of theta and hyperbolic cosine of theta will represent respectively the y and the x coordinates, but not on the graph of a circle, but on the graph of a hyperbola. Hence the name hyperbolic sine, hyperbolic cosine. So this graph will not be nearly as pretty, so I apologize in advance. So, oops, I don't like that or that. So let's see here. If I drew a y-axis and an x-axis, and maybe I drew in this lovely hyperbola. Please forgive the...
Hyperbola.
That's not too bad. That'd be like the right half of a hyperbola. You know, the left half would be over there. I'm just going to focus on the right half. So, for a particular hyperbola, if I maybe started here at the origin, so the angle has to go from the origin, and I drew like this, I continued this little angle out to here, let's say, and we're going to call this angle, as before, we're going to call that theta. Then the point on the hyperbola would simply be hyperbolic cosine of theta, comma, hyperbolic sine of theta. Okay? So why did they choose, when I say they, I mean like our forefathers and mothers of math, why did they choose to make cosine and sine, like circular cosine and circular sine? Why do they choose to make that the thing that we focus on the most? Maybe it's because they thought circles were more common than hyperbolas. And so they thought, you know what, let's focus on circular versions of these instead of the hyperbolic versions. I don't know. But this is just as valid and could be even more useful to you depending on what you major in and study and become a professional at. Who knows? I do know, you guys know World War II history? You guys know like the German submarines like threatened to like derail everything? So the Allies actually used hyperbolas to figure out, hyperbolic patterns to figure out where the German submarines were. I'm recalling some old math history, and forgive me for not knowing the details, but it just like popped into my brain. Would be worthy of a read, right? Would be worthy of a little research. But they found that if they could track the sounds coming from these German submarines, and they knew the focus of these hyperbolas, they could then calculate where the German submarines were. So some early work with sonar, of course. But anyway, so that's kind of the basic plot of like why it's called hyperbolic sine and hyperbolic cosine. Okay. Now, what are they? Here are the actual expressions for these functions. right here. So if you graphed these functions independent, like where the independent variable is x instead of theta, so if you actually graph these on the xy axis, then they look like this. And maybe take a minute here. I think I write something about this. Yeah, take a minute, get your calculators out, and look at what the graphs of these look like. They're obviously really, really similar, right? There's only one positive, negative change of difference between these two, so they're extremely similar. So take a minute, look at what the graphs look like on your calculator.
Is there like a fast way to get hyperbolic sine and just
I think, I think there is. I think it's in your. I want to say in the catalog of your calculator, like down low. It's like there's a catalog button, like down there. It's like a shift off the numeric stuff, or down below.
Oh, I see it.
I think there is. I think you can get like hyperbolic sine and cosine down in there somewhere. It might be faster just to enter that, because like the catalog, you got to scroll forever. And
I'm surprised you can't do like alpha S to go to the S.
I tried that. Yeah. Did you find it in the catalog?
They have copies.
Yeah, it's in there somewhere. There you go.
How does it look? I want it, Tammy.
Whatever you need to remember it.
Where can you find it?
Catalog, but then you got to scroll forever, so it might be faster just to enter those.
Okay. Oh, here's a coach. Oh, you can do it inverse. Oh, yeah.
You can do an inverse cosh. Yeah.
Or they can use something like
I went up.
They've seen, I'm not sure if the pictures are finished, but they saw, they had pictures of the characters all wearing like a contraption that looked like this, and it had like something green right here, and it was like a,
So,
it was like turning back.
correct me if I'm wrong, but doesn't hyperbolic cosine look a little parabolic-ish? Looks somewhat. Is it? I can't remember. Does it have the vertex-looking thing at the origin? Or is it up at? Well, it's up at 1. Y equals 1. Yeah. Okay. So this one looks roughly like that. Oops. Should be having some symmetry there. And then hyperbolic sine, I know, looks sort of like a cubic, doesn't it? And maybe if you graphed them on top of each other, did you notice that they seem to coincide for a while? Seems like they kind of do one of those, sort of. Anyways, lots of interesting things there. And I would say, just to be honest with you, this is another one of those crazy moments where you're like, why does E just keep showing up? Right? Like, how is E related to cosine or hyperbolic cosine? How is E related to a hyperbola? Right? There you go. So anyways, just some things to notice about those graphs. You can see that, hey guys, some cool connections here. Do you guys know that cosine, like regular circular cosine, has y-axis symmetry? Do you see how the same applies for hyperbolic cosine? And doesn't circular sine have origin symmetry? And do you see how hyperbolic sine also has origin symmetry? There are a lot of similarities, and obviously some very important differences, but a lot of similarities between these two. And, of course, you can see that the elements of them are quite similar as well. Just that 1 minus the plus changes everything as far as how the graphs look. Okay, so what I thought we could do here is a couple of examples and then a little bit of calculus. You'll find the calculus to be very straightforward, I think. Based on what you've done, I don't think you'll find this to be too tough. So, let's see here. We'll go with that. Okay, so based on these formulas, Guys, based on these formulas right here, let's see if you guys can evaluate hyperbolic cosine of 0. Hyperbolic, just focus on number 1 for a second. You got the formulas right there. Please think of this as a no calculator activity. Seriously, see if you can calculate the hyperbolic cosine of 0. I need to do attendance really quick. They get upset if you don't do it right away. Okay. Whoops. Okay. So hyperbolic cosine of 0, if done absent the calculator, would be e to the 0 plus e to the negative 0 over 2. Well, e to the 0, just 1, right? So essentially I have 1 plus 1 is 2. 2 over 2 is 1. So they actually share kind of a common output there, input-output with cosine, right? Because the cosine of 0 is also 1. But that would be the only point. From there on out, they're going to be quite different as you think about the graphs, perhaps. And then number 2 here says, if hyperbolic sine of x equals 3/2, evaluate hyperbolic cosine of x. So if this were like a circular sign, you could just build a triangle and have this done pretty easily. But these are not based on triangles within circles. These are based essentially on locations of points on hyperbolas, so the same principle doesn't work. I put in here, we'll use a well-known identity. So you guys know this identity, and I'll be very careful to write circular functions here. So for circular functions, cosine squared plus sine squared equals what? 1. So for hyperbolic trig functions, it's slightly different. It's hyperbolic cosine squared minus hyperbolic sine squared equals 1. Okay, so just slightly different relationship. You can actually think back to those graphs, and you can see perhaps how that would work with the graphs as well. So anyway, so we would say, hey, if hyperbolic sine is 3/2, we could just plug that in right here and say, well, that's 3/2 squared. And this is still hyperbolic cosine squared. And now it's just a matter of a little arithmetic, knowing that identity would be everything here, right? Not knowing it would also be everything in a bad way. So that's 9/4, or negative 9/4. If you add that negative 9/4 over, you get 13/4. So hyperbolic cosine squared is equal to 13/4. You square root both sides, and you get hyperbolic cosine of x equals root 13 over 2 plus or minus that. So anyways, so just some different relationships. The idea being you've never seen this before. Hopefully this will help at some point in the future. And if it doesn't, well then now you know something a little bit more than you did before. Okay, so I got about 5 minutes, and we're actually going to do a little bit of calculus here. It's really easy. So here we go. Calculus with hyperbolic trig functions. So this, of course, is going to be a little bit different from circular trig functions. The derivative of hyperbolic sine is hyperbolic cosine. Probably will not be a super huge surprise there. So the slope of hyperbolic sine is equal to the y value of hyperbolic cosine. And then, believe it or not, the derivative of hyperbolic cosine is equal to positive So there is no sign change like you
Is
see.
there, do they all also, are they all multiplied by the derivative of u as well?
Right, exactly. So yeah, times du dx. Yep. Chain rule factor times du dx. Absolutely. So that chain rule is always with us. You're right. Okay. So that being said, number 3, derivative with respect to x of hyperbolic cosine of 5x squared minus 10x. Give that one a shot. We'll take a look at number 4 as well. So again, you'd want to recall, of course, that the derivative of hyperbolic cosine is hyperbolic sine with the inside still intact. And then you would multiply by the derivative of that inside 10x minus 10 according to the chain rule principle. So then finally number 4 is an integral. And so this ties in really nicely with chapter 4, that unit 2 we just covered. We could rewrite this a little bit. You could say that this first factor is really hyperbolic cosine of x minus 1 quantity squared times this hyperbolic sine of x minus 1. If that's the case, you can clearly see we have a product. And not only that, but we've got some composites, right? So what I would look at over here on the left is I would look at this inside right here, and I would say, well, that's clearly an inside function. And the question is then, is the other factor the derivative of that? In other words, did Timmy mess this up? Colin? Timmy did not mess this up for once, right? Isn't the derivative of hyperbolic cosine just hyperbolic sine? And the chain rule factor is just a 1, so we're good with that. So there is no mistake here. In other words, this on the right is the exact derivative of the inside of the main composite here.
You still messed it up though, didn't you? The other one?
The other one?
The cosine of h? Should be 1/3 and then outside when you take the integral of it?
Well, we haven't finished. Yeah, we haven't finished it yet.
We're still mixed up.
No, that's just a power rule. That's just power. You're trying to throw Timmy under the bus, aren't you? Yeah, that's just our power rule for integrals.
Okay.
So it would end up being 1/3 times the hyperbolic cosine of x minus 1 quantity cubed, and then don't forget the plus c. That still applies. So you could differentiate this using the chain rule, and you'd see that hyperbolic sine of x minus 1 coming back out according to the chain rule. This just went back inside where it came from. It's the derivative of the inside. No, the antiderivative should be of the squared only. When you have these composite functions, the only thing you actually antidifferentiate is the outside function, in this case, the squared. Does that make sense?
Yes.
As long as your du, as long as your other stuff is correct, in other words, Timmy didn't mess up, the only thing you do is you antidifferentiate the outside function.
I know, I didn't realize that.
All right.
After I did it.
Hope you feel a little smarter today. Have a good one. See you tomorrow.